Welcome to QOD video number 50. So an important milestone. We're up to 50 QODs. Who knows how many more we'll have. Yesterday I went on a bike ride and I did something that I extremely rarely do on a bicycle ride, which is to stop and take a picture of myself. And pretty much anytime I take a picture of myself on the bike, I come up with this sort of dorky looking guy on bike face. But the important thing was that I was at Chaw Road. So today's watchword is Ivy Chaw Road, that is. Okay, so what are we going to talk about today? Well, before we get into what I'm actually, the main meat of what we're going to talk about, I just wanted to mention a couple things. I may have already done this in a video. I may have just mentioned it in passing in class. And so I just wanted to go through two slides really quickly. Just to say, when it comes to shapes and bond angles, there's a difference in size between a bonding electron pair and a non-bonding electron pair. The non-bonding electron pair is larger. And so when you have a molecule that contains one or more non-bonding pairs, and here we're comparing methane to ammonia to water, you will see that those larger non-bonding pairs will squeeze the bond angle a little bit. So methane has the ideal bond angle for tetrahedral of 109.5 degrees. For ammonia, which has one non-bonding pair, that HNH bond angle has now been squeezed to 107. And for water, which has two, that HOH bond angle has been squeezed to 104.5. You do not have to memorize or predict numbers like this, but you ought to be able to say on the AP exam that, for example, water has a bond angle that is slightly less than 109.5. And then I think this has come up as well, and that is that a double bond or a triple bond is also larger, has more electron density than a single bond, and so that they will squeeze bond angles as well. So you can see in this model of phosgene, is the name of this molecule here, that the OCCl bond angles are larger than the ClCcl bond angles because these ones contain a double bond. Okay, the main thing we're going to talk about today is we've talked about drawing Lewis structures and we've talked about shapes of molecules. We haven't really talked much about what the nature of covalent bonding is. We've talked about the fact that a bonding pair is shared between two atoms, but we haven't really talked about how that actually occurs. And so we, because we think of bonds forming through sharing of electrons, that can really only happen if you have overlap of the orbitals of the two atoms that are bonding. So for example, if I'm going to make an H2 molecule, that really requires me to have the 1s orbital of one hydrogen atom overlapping with the 1s orbital of the other hydrogen atom. That creates an overlapping space in between in which two electrons can be shared. And we can think about this in terms of one hydrogen atom having a 1s orbital that's only half occupied, and the other hydrogen atom having a 1s orbital that's only half occupied. And so they can in that case, two half occupied orbitals can overlap, and that will give us a shared electron pair. We can think about this for more complex atoms. So for example, here's the orbital energy diagram for chlorine populated with its 17 electrons. And you can see that at the valence level, I've got three orbitals that are completely filled, but I have one orbital that is only half filled. So that 3p orbital could overlap, say, with another 3p orbital from another chlorine atom, that you would get overlap between this orbital and the same orbital on another chlorine atom to give you, again, a shared pair and a bond between the two chlorines. And you can imagine overlap between atoms of two different elements. And so here is a 3p orbital for chlorine that's only half filled, and a 1s orbital for hydrogen that is only half filled. And so these can overlap and give you a shared pair of electrons and a hydrogen-chlorine bond. That works well when we're talking about these diatomic molecules, but it really breaks down when we start talking about anything more complicated, and even something as simple as uh, methane. So let's think about methane for a second. That model we were just talking about works for the hydrogens. So in other words, I've got 4 carbon-hydrogen bonds here, and so each of those is going to come from an overlap of an orbital from carbon and an orbital from hydrogen. And so that's hydrogen works just fine. Each hydrogen atom has 1 orbital that's half filled, and so that's all ready to go when it comes to bonding. The problem lies with the carbon atom, because if you look at the valence shell of carbon, it does not have 4 orbitals available for bonding. It has a completely filled 2s orbital, and then two 2p orbitals that have electrons in them, and then a completely empty 2p. And so that's one way in which it doesn't really work. Suppose you said, though, well, what if we just gave this a little bit of extra energy, and so we could promote, say, this electron up into this orbital? Wouldn't that give us 4 half-filled orbitals that would allow us to make a methane molecule? Well, in one sense, yes, but the other problem with this is the shape, right? So let's just say that we did that. We promoted the electron from the 2s. We promoted one of those electrons into the empty 2p. We still have a shape issue, right? Because as you'll recall from chapter 6, actually, a 2s orbital is spherical, and then these 2p orbitals are actually have 2 lobes each, but they lie along orthogonal XYZ axes. But we know from the VSEPR stuff that we talked about in chapter 9 that methane is actually a tetrahedral molecule, and so you can't get tetrahedral out of these orbital shapes here. So something else has to be going on, and that something else is what's known as orbital hybridization. So I'm going to define orbital hybridization, and then I'll go through some examples, specific examples of the 3 types of orbital hybridization we're interested in. And then further on, some examples of molecules exemplifying those 3 types. So orbital hybridization, at any given principal energy level, s and p orbitals can combine. That is, s and p orbitals that are part of the same principal energy level. They can combine, or we say hybridize, to give an equal number of what we call hybrid orbitals that can be used for bonding. And there are 3 possibilities. There are more than 3 that your textbook cover, but in terms of the College Board curriculum, I'm only just going to focus on 3 possibilities. That is what are called sp orbitals, in which 1 s orbital and 1 p orbital hybridize to give 2 hybrid sp orbitals. We can also have sp2 orbitals, and that's where 1 s and 2 p orbitals hybridize to give a total of 3 sp2 orbitals. And then we can have what are called sp3 orbitals, in which 1 s and 3 p orbitals hybridize to give 4 sp3 orbitals. This can occur at any principal energy level in which there are both s and p orbitals, and so that means anything from principal energy level 2 on up. And you'll notice that the designation here simply determines how many. There's only ever 1 s that can go in, and then the number of. Oh, well, you might have just heard the fire alarm going off in the background, but I magically made that fire alarm disappear. So again, the S represents the fact that in any of these hybridization events, 1 s orbital is going to go in. And then depending on how many p orbitals go into the hybridization, that's the superscript after the p. So let's take an example. Let's take a look at some examples of this. Suppose we wanted sp hybridization. And so this, I'm just going to consider something that is in period 2. So this would be this would be all possible core and valence orbitals for an element in period 2. And so suppose I want to do sp hybridize this. I would take 1 s orbital and 1 p orbital. They would hybridize together to make 2 sp orbitals. So now instead of a 1s, a 2s, and 3 2ps, I've got a 1s, 2 SPs at the 2 level, and 2 Ps at the 2 level. Now, when that happens, what I'm doing is I'm taking the s orbital from 2 level and a p orbital from the 2 level, and I'm hybridizing them. That gives me the number of orbitals that go in equals the number of orbitals that come out. They look like this with a large lobe and a small lobe. If often when we draw these things, more than one orbital at a time, we just leave the small lobe out just because it can be a little bit confusing to try and draw things that are overlapping each other. But when you have sp hybridization, these two sp orbitals adopt an orientation where they're 180 degrees apart from each other, just like this. So this is the large lobe of one, this is the large lobe of the other. If we wanted sp2 hybridization, again, here's our generic period 2 element and its orbital energy diagram. In this case, I would take now an s orbital and 2 p orbitals because I want to make 3 sp2s. I hybridize those and I get my 3 sp2s. The 2 here means it's at the n equals 2 principal energy level, and 1 p orbital. You'll notice that these orbitals, and this is true in the previous slide as well, when you hybridize orbitals, their energy is intermediate between the orbitals that you use to get them. And so the energy of sp2 orbitals, just like the energy of any hybrid orbitals, is going to be greater than the s, but lower than the p that were used to form them, and they'll be degenerate with each other. So when we do that, we get 3 hybrid sp2 orbitals now. They have that same sort of large lobe, small lobe look about them, and they adopt a planar orientation in which they are 120 degrees apart from each other. Finally, I could do sp3 hybridization, in which I'm going to take the s orbital from the 2 level and all 3 orbitals from the p orbitals from the 2 level, and hybridize them into a degenerate set of 4 sp3 orbitals, which again are intermediate in energy between the s and the p's that I use to form them. In this case, I am now generating 4 hybrid orbitals that once more have this large lobe, small lobe look about them, and they lie along the 4 points of a tetrahedron, just like this. And so it may kind of have dawned on you then what sort of central atom arrangement is associated with each one of these particular types of hybridization. sp3 hybridization gives you 4 orbitals in a tetrahedral arrangement, so you would use that when you had 4 electron domains. sp2 hybridization gives you 3 orbitals in a trigonal planar arrangement, so that's the hybridization that's associated with when you have 3 electron domains around the central atom. And then finally, sp hybridization gives you 2 hybrid orbitals in a linear arrangement, and so that's what you're going to use when you've got a central atom that's got 2 electron domains. Okay, let's look at some specific examples. And this one example that we could use for sp hybridization is beryllium hydride, so BeH2. It's impossible to draw a Lewis structure for BeH2 without having an electron deficient beryllium atom, and it's just the way it goes for beryllium. And so there are only 4 electrons in its valence shell, but you can't give it any more than that. And so if we were making a model of beryllium hydride, it would be linear like this because there are only 2 electron domains around the central atom. And so that would be formed by an sp hybridized, and so we would have taken 1 s and 1 p orbital to make 2 sp hybridized orbitals. Beryllium has 4 electrons total, so when we populate the orbital energy diagram, I now have my hybridized orbital each half-filled. I've got 2 hydrogens I can use, each with a half-filled orbital, and so I'm going to get overlap, that hydrogen with that s hybrid orbital, that hydrogen with that hybrid orbital, and I will get my beryllium hydride. Simplest example of sp2 hybridization would be what's called borane, or BH3. Here again is a Lewis structure of BH3. It is once more impossible to give boron a full set of 8 electrons, and so it is going to be electron deficient. It is a trigonal planar molecule. It looks like this. So now instead of sp hybridized, I am sp2 hybridizing, taking the s at the 2 level and 2 of the p's to make 3 sp2 orbitals. Boron's got 5 electrons, so when I populate the orbital energy diagram, I've got 3 half-filled hybrid orbitals. I can bring in 3 hydrogens with their half-filled 1s orbitals, and I can get overlap to give me this molecule. And then the example for sp3 would be methane, which is where we started this whole conversation. So my carbon, and that is tetrahedral, as we mentioned. And so in this case, because I got 4 domains around the central atom, I am going to sp3 hybridize. That gives me 4 degenerate sp3 orbitals. When I populate that with the 6 electrons of carbon, I get 3 half-filled orbitals at the valence level. I'm sorry, 4 half-filled orbitals at the valence level. I can bring in 4 hydrogens with their half-filled s orbitals. I can get the overlap I need. I've got the shape I need. I've got my methane molecule. So just to sort of recap here, I'm going to use sp hybridization if I've got 2 domains for a linear shape. I'm going to use sp2 hybridization when I've got 3 domains for a trigonal planar shape. And I'm going to use sp3 hybridization when I need 4 domains for a tetrahedral shape. All the examples I've given you so far, all of the hybrid orbitals only had exactly 1 electron in them, half filled. It's possible to have other arrangements. So for example, for ammonia, we'd look at this and we'd say, well, it's got 4 domains around the nitrogen, even though one of them is non-bonding. That means I need sp3 hybridization. But now I've got 5 valence electrons instead of 7 total, but 5 valence electrons, and this should be an N here, not a C. My apologies. And so what happens now is at this sp3 level, I've got 1 completely filled orbital. That's the non-bonding pair, and then 3 half-filled, which can then accept overlap with 3 hydrogen atoms to give me these 3 nitrogen-hydrogen bonds. Again, apologies, that is supposed to be an N, not a C. Just really quickly, and then I'm going to wrap this up. Hybridization is a big player in what's called the valence bond theory model of bonding. And so we talked about overlap, and so I'm just going to very quickly talk about the 2 different ways in which orbitals can overlap to form bonds. The first one's called a sigma bond, and a sigma bond is characterized by head-to-head overlap. The overlap and the electron density are on an axis between the 2 nuclei, and this can involve any type of atomic orbital. So back earlier on, we looked at an overlap between 2 p orbitals that's end-to-end. That would be a sigma bond because the overlap is between the 2 nuclei. We could have bonding not just between a p and a p, but between a p and an s. Again, the overlap is on an axis between the 2 nuclei. We could have a couple of s's overlapping with each other. Once again, the overlap is on the axis. Or we can have overlap between hybrid orbitals and unhybridized orbitals. So here in methane, we've got each one of these bonds consists of an overlap between an sp3 orbital of carbon and an s orbital of hydrogen. As long as the overlap is on a axis between the 2 nuclei, it's end-to-end overlap. That is a sigma bond. The other type of possibility is what's called a pi bond, and that instead of being end-to-end overlap, that is side-by-side overlap. And what that means is that the electron density, the overlap in the electron density now is not between the 2 nuclei, but above and below the internuclear axis. And whereas sigma bonding can involve any kind of orbital end-to-end overlap, pi bonding can only involve p orbitals. So I've just pulled from the internet a couple different representations of pi bonding. Here are 2 adjacent carbons with p orbitals in them overlapping to give you this sort of product, which is electron density above and below the internuclear axis. Here's a view sort of right along that internuclear axis or directly perpendicular to it. You can see one p orbital and a p orbital on a second adjacent atom, giving you once again that electron density above and below the two nuclei. We'll talk about this some more because this answers the question of that I haven't addressed in this video, which is where are those leftover p orbitals? If I've got p orbitals left over from sp or sp2 hybridization, where are those p orbitals and what are they doing, and what happens if one of my electron domains is a double or triple bond? So we'll talk about those things in class. Otherwise, until then, thanks for watching, and we will see you soon.